My name is Zach, and I'm a graduate student in the Panetti Lab. I'll be using light catalysis to make carbon dioxide, a common waste gas, into more useful molecules. Certain materials used in the right way can promote unique transformations in otherwise useless or harmful molecules. These catalysts can be found everywhere, such as in our car's catalytic converters. In 2020 to 2022, an organized crime ring hit the United States, where catalytic converters were removed from thousands of automobiles. The thieves were interested in the small quantities of rare metals like rhodium, palladium, and platinum, which could be resold. These catalytic converters are expensive to replace, costing several thousands of dollars each. Now, why are we paying to make our cars more expensive? Why do our cars need trace quantities of precious earth metals? Catalytic converters do what their name implies. They convert harmful combustion products into less harmful gases using catalysis. While combustion is often shown to take hydrocarbons found in gasoline or oil and the oxygen and air to carbon dioxide and water, combustion isn't always a clean process. Sometimes the burning is incomplete, and sometimes other molecules that aren't supposed to get involved find their way into the reaction. For dangerous gases from incomplete burning, combustion also produces carbon monoxide that interferes with oxygen absorption in our blood. Breathing in too much CO will chemically suffocate you. Additionally, combustion also produces carbon particulates, basically unreacted fuel released as soot. These pollutants are harmful for the environment and have been shown to cause lung issues and increase your risk of cancer. Lastly, combustion also produces NOx gases, typically either NO or NO2, from the nitrogen that is always in our atmosphere. These gases are a major component of smog. Since these products are very difficult to stop producing and are bad for our health and the environment, we need a way to destroy them before they can escape into the atmosphere. The metals in the catalytic converter do just that by converting these harmful gases into less harmful gases, CO and soot into CO2, and NOx species back into N2 and O2. Normally, these reactions are difficult to perform but are relatively easy in the presence of these metals. When something added to a reaction helps a reaction occur and are present at the beginning and end of a reaction, we call these chemicals catalysts. While this is a huge oversimplification, catalysts do either one of two things. 1. Let reactions that are normally hard to achieve occur much quicker and with less energy input. Or 2. Let reactions occur that would otherwise not happen. A good way to think about catalysis is like a crosswalk. Under normal conditions, with cars traveling on the road, it can be dangerous for pedestrians to cross, which can cause a buildup of people on both sides of the road. Introducing a crossing guard can increase the flow of people from one side of the road to the other, like how catalysts can speed up reactions. Alternatively, you can place a crosswalk on a part of the road that cars do not normally stop at, creating a new path for pedestrians to travel, like how catalysts can initiate new kinds of reactivity. Back to the example of the catalytic converter. Gases like CO and NOx are relatively stable, but CO2 and N2 are even more stable. However, changing CO and NOx into CO2 and N2 often take a lot of energy. However, the expensive metals in a catalytic converter enables these reactions to occur much easier. Beyond our cars, catalysis is everywhere. Proteins in our bodies and in all living things are catalysts that allow life to happen, from nerve signaling to your brain, plants photosynthesizing, and the changing of food into ATP in the powerhouse of the cell. For example, glycolysis is a process that converts chemical energy from sugars and carbohydrates into cellular energy. There are several enzymes, each with specific functions. They work in tandem to create a beautifully complex concert of chemistry and catalysis to keep you alive. Catalysts can be good, but they can also do bad things. Depletion of the ozone layer was catalyzed by the now forbidden chlorofluorocarbons, sometimes called CFCs. These were used heavily as coolants, flame retardants, and among other things. Ozone absorbs a significant amount of skin cancer-causing UV radiation from the sun, and these chemicals will prevent its formation. These CFCs were phased out to prevent further destruction of the ozone layer. Catalysis has been shown to be so important that the Nobel Prize Committee has awarded it multiple times over the past 100 years, for accomplishments that have, in quote, conferred the greatest benefit to humankind. We start all the way back in 1909 to Oswald for early work on catalysis, then in 1912 to Sabatier for early hydrogenation catalysis, then in 1961 to Calvin for the light-independent cycle of photosynthesis, then 1963 to Ziegler and Natta for catalyzed polymer chemistry. 1972 to Anfinsen, Moore, and Stein for work on ribonucleases and their catalytic activity. Then in 1989 to Altman and Czech for catalytic properties of RNA. 1993 to Mullis for inventing the PCR method to catalytically replicate DNA. 2001 to Knowles, Nouri, and Sharpless for chiral catalyzed hydrogenation and oxidation reactions. 2010 to Heck, Negishi, and Suzuki for palladium catalyzed cross-coupling reactions. Then finally, in 2021 to List and Macmillan for asymmetric organic catalysis. If we broaden our definition, we can include many more. Catalysis helps the world run much more smoothly and efficiently. Without catalysis, many of the reactions that occur on the daily would require so much more energy. Many products we take for granted would be so much harder or even impossible to come by. So when you drive a car, use a plastic bag, or even eat an apple, think of all the exciting chemistry that enables it all. With that, I appreciate you taking the time to listen. If you would like, please comment any more questions about this. Please check out the group's website at panetti-lab.com. I'm Zach Garcitis, and if you'd like to see us cover another topic, let us know.